Thank you for the introduction. I would like to thank the organizers for giving me this opportunity to be part of this distinguished workshop. So the talk that I'm going to give is a bit of like a different flavor, and it's based on a recent joint work with Martin Dingdosch and Joe Pfeiffer. So we worked on this LP regularity problem for parabolic operators, but this problem is actually first considered for the elliptic equations. So let's go over that first. So what's the setup? I will take a domain omega in Rn, and for the simplicity of the talk, I will assume that this is an unbounded domain above a Lipschitz graph. But many of these, well, all the formulations, all the results can be formulated for the bounded Lipschitz domain as well, and even on more general domains. So the matrix A is an n by n matrix, consists of bounded and measurable functions, and it satisfies this ellipticity condition. And we will consider the elliptic operator in divergence form. All right, so this is the elliptic setup. Now the LP Dirichlet problem for p between 1 and infinity is defined as follows. So ultimately, we want to consider this problem for LP boundary data. To start with, we say that the LP Dirichlet problem is solvable for an elliptic operator L on the domain omega. If you take any compactly supported continuous function, you can find a solution that solves the Dirichlet problem, but with an LP bound on the non-tangential maximum function of the solution. Okay, so what this U is a non-tangential maximum function, which is you take the supremum of the value of U in a cone in omega. Okay? So I put a quotation mark there because if the boundary of the domain is not a plane, then the cone is really not a cone, but it's like twisted. But it's the same spirit of a non-tangential access region. Now, the good thing about this, knowing this LP bound, is that if this DP LP Dirichlet problem is solvable, then for any LP function on the boundary, you know that there exists a unique solution to this equation in omega such that the non-tangential maximal function is in LP and U converges to the boundary data F non-tangentially almost everywhere. All right. So next, I want to formulate LP regularity problem, which is essentially like a Dirichlet problem, but with more regular data. So we say that the LP regularity problem is solvable for an elliptic operator if whenever you take a compactly supported smooth function G, you can find a solution to still the Dirichlet problem, but with an LP bound on the non-tangential maximum function on the gradient of U. Okay? Now, since I don't assume anything on the coefficients yet, it's just bounded and measurable, not even symmetric matrix, we don't know whether the gradient of U is locally bounded. So we have to modify our definition of the non-tangential maximal function a little bit. So instead of taking the supremum we still take the supremum on a cone, but instead of evaluating the gradient of U on the point, we evaluate on a ball centered at the point, and it's basically a Whitney ball. So it's a ball centered at a Y and with radius comparable to the distance to the boundary. So it's an average. All right, so here we control this LP norm of the non-tangential maximum function of gradient by the LP norm of the tangential gradient of the boundary data. Now, if the domain is more general than Lipschitz, then this has to be replaced by the Hawash gradient. But since I'm not going to talk about more general domains in this talk, so let's just leave with this. All right, so what do we know about the solvability of the Dirichlet problem and regularity problem? So first, I want to ask what are the sufficient conditions on the elliptic operator for like the LP Dirichlet problem is solvable or for the LP regularity problem is solvable. Well, it turns out that it's not only just about smoothness. Okay, it's not only about smoothness in the following sense. So there are counterexamples showing that the LP Dirichlet problem may fail for any P, okay, even for an operator having smooth coefficients on smooth domain. And it's an example constructed by Modica and Motola, and actually they just consider the upper half space, and the coefficients are smooth inside of the domain, but not onto the boundary. So if you have actually smooth all the way to the boundary, then you know everything is nice. On the other hand, the LP Dirichlet problem may hold for some P, even when there's no regularity on the coefficients at all. So you can see this kind of examples when you also consider the upper half space, but the coefficients does not depend on the transversal variable, but you don't need to assume anything else than that. Okay, so because of this, the condition that we will be focusing on is about a bit different nature than the smoothness. The condition that people studied is a Carlson measure type condition, and it's also referred to as Dalberg-Koenig-Pfeiffer condition. So it assumes that basically the gradient of the matrix A squared times the distance to the boundary is the density of a Carlson measure on omega. If you haven't seen Carlson measure before, it means that you can find a constant such that this quantity is bounded. Okay? And also, we require that the gradient of A times the distance to the boundary to be uniformly bounded. So A is locally Lipschitz, but the gradient of A might blow up near the boundary. This is so this condition is also stable under a bi-Lipschitz change of variable. And this is in particular important when you think about this problem on Lipschitz domains. All right, so what do we know about the LP Dirichlet problem? Because I have only limited time, so I will just tell you the state of art. So if we focus on the class of operators that I talk about that satisfy this Carlson condition, then we know pretty much about the solvability of the Dirichlet problem. And they can be summarized in two regimes, namely the large constant regime and the small constant regime. So in the large constant regime, where we assume the matrix just satisfies this Carlson condition or the DKP condition, and what we know is that the LP's Dirichlet problem is solvable for some P. So we don't know for what P exactly, but for some P and potentially large on Lipschitz domains. And this result actually can be generalized to more general domains like Cordock domains. And in a small constant regime, we assume that the DKP condition is kind of has a small constant, has small constant, meaning that if in the limit case, if you assume something like the vanishing Carlson condition, then you actually get the LP solvability for the Dirichlet problem for all P bigger than 1 on C1 domains. Now, if you want to stick to Lipschitz domains, then you know that LP Dirichlet problem is solvable for P greater than or equal to 2. So for the Laplacian, Laplacian falls into this category, okay? And for the Laplacian, it's actually this result is known quite early, in 1977 by Dalberg. Okay? So actually, for A satisfy the vanishing DKP condition, this kind of result is not written, but I believe it's true. It's just no one has really written. And the range is sharp in the sense that for any P smaller than 2, you can cook up a Lipschitz domain that the LP Dirichlet problem for that P is not true. It's not solvable. Okay, so what do we know about the LP regularity problem? the way to understand the regularity problem, okay, so first, the regularity problem is harder than the Dirichlet problem, because if you know the RP, so LP regularity problem is solvable, then you actually know that the LP prime of the Dirichlet problem for the adjoint operator is solvable. Now, and this is due to Koenig and Pfeiffer in 1993. Now, the converse is more subtle, and actually it's an open question that this implication is still open if you don't assume anything. But there's some partial converse. So the first result says that if you know that the LP regularity problem is solvable for some P, then the LP prime Dirichlet problem is solvable for the joint operator implies the LP solvability of the regularity problem for L. Now I wrote here R1, even though I didn't really define R1 because it's the P, I said it's bigger than 1, but the reason why I put R1 here is because there's a result says that if we know RP holds, and if P is greater than Q, then RQ also holds. So assuming R1 is, you are placing the least assumption there. So very recently, there's a big breakthrough in this area, which is people show that in Lipschitz domains, and even more general, if you assume this DKP condition on the operator, then this direction also holds. So that VP prime implies RP. And this is independently obtained by two groups of people. So for the first, okay, so Mogul, Poggi, and Tosa, they obtained this direction on more general domains than Lipschitz. And Dingdosh, Hoffman, and Pfeiffer, they obtained this result on Lipschitz domains. And I think this is blocked here. And later, by a different method, Finney gave a shorter proof of this direction in Lipschitz domains. And the methods actually are quite different. All right, so these are what we know about the elliptic case. Now, what about parabolic case? So let's start from the beginning again. How much do we need to change the setup? The first, the domain will be a space-time domain. And for simplicity, I will assume that so the domain does not vary in time. And so it's a Lipschitz singulator where this O is a spatial domain Rn, is an unbounded domain above a Lipschitz graph. And now the matrix depends also on time, and we still assume the ellipticity condition. And we consider a parabolic operator in this form. And because of this parabolic scaling, when we talk about distance, I will be using this parabolic distance, which is adapted to the parabolic scaling of this equation. All right, so now let's formulate the LP Dirichlet problem for the parabolic operator. Almost everything is the same as the elliptic case. The only thing I want to mention is maybe when you take the non-tangential maximal function of U, right? The non-tangential maximal function is taken in a cone, but now we have to consider the parabolic cone. And if this is the t direction, is the time direction, then the slope of this cone here in the t variable kind of blows up near the boundary because this is essentially the graph of the square root of t. But that does not change much of the problem. And okay, but for the LP regularity problem, you need to be more careful. So we say that the LP regularity problem is solvable for a parabolic operator if, again, for any compactly supported smooth function, we can find a solution that satisfies the equation and the boundary data on the boundary. This is parabolic. So starting from here, I'm talking about only parabolic. Okay? Now, for the LP bond of the non-tangential maximum function, you have to be careful because now we have the time variable. So on the right-hand side, I want to include not only this tangential derivative in the spatial variable, but I also want a half derivative in time. Okay, and this is the homogeneous Sobolev parabolic Sobolev norm. And here on the left-hand side, I still have the LP norm of the modified non-tangential maximum function of the spatial gradient of the solution. Now you might ask me why you don't want to control also the LP norm of the non-tangential maximum function of maybe the half derivative in time of U. And that's because in a recent work by Dingdosh, he showed that the LP norm of the non-tangential maximal function of the half derivative in time of U can be actually controlled by the non-tangential maximal function of the gradient of U plus the boundary data. So, yes. Yeah. And yeah, actually, and he showed this for like a parabolic operator with a drift, but yeah, so the solution space but so you mean you want to use the equation to okay, yeah. So yeah, I guess sure. I think definitely use it somewhere in this proof. Yeah. Yeah, so because of this, we know that if the LP regularity problem is solvable, then we actually have the LP control on both the gradient of U and half derivative. Okay, so that's the definition of the problem. Now, what do we know about them? Still, we are going to consider focusing on this DKP condition, which is a Clausen condition, but in the parabolic setting. I will give you the details later. But if you consider that assumption, then basically for the Dirichlet problem, the results essentially are the same as the elliptic case. So the only thing so again, there will be like the large constant regime and the small constant regime. The only thing maybe I want to mention here is that for the Dirichlet problem, people can even do the time-varying domains with some conditions also on the t variable. And they can consider the operator with a drift because when the domain changes as time, this is the natural class of operators to consider. All right, but I will not go into too much of the details of these. Now, what about the regularity problem? For the regularity problem, I will return to this parabolic operator in divergence form, and I will keep the domain to be time invariant. Now, if you look at this diagram, it basically says we kind of bring the parabolic case to the elliptic standards. So, but these are much more recent. So for the regularity implies Dirichlet, this is done by Dingdosh and Dyer in 2019. And for this partial converse, assuming you know the solvability of RQ for some Q, is a preprint by Dingdosh and Satterqvist. And the work that I did with Dingdosh and Pfeiffer is that we show that if you assume the DKP condition in the parabolic setting, we have dP prime implies RP. So this is the main result that I want to talk about. So here, this is this main result formulated again. This is the operator, and the domain is Lipschitz cylinder. We assume this, so this is basically the parabolic Clausen condition that I mentioned. before. The only difference between the elliptic setting is that we will also assume that the t derivative of the matrix also satisfy this Carlson condition. So if you take the dt of A and squared, and now because of the scaling, you will have the distance to the boundary cubed. So we assume that this is a Carlson measure on omega, and we have an L-infinity bound of the gradient and the t derivative of the matrix. So then, assuming these conditions, we know that there exists a P naught greater than 1, such that the LP regularity problem for the operator is solvable for P between 1 and P naught. Now, because of the partial converse result by Dindolch and Satterbeast, we know that if we have a P naught for which this is solvable, we know that this range is exactly the dual range of the solvability of the Dirichlet problem. So this result is actually sharp. All right, so I will talk about any questions before I move on to the proof. Yes. So this P naught, so the question was, what does this P naught depend? So this P naught will depend on the Carlson norm here. It will depend on the ellipticity condition, as well as this L-infinity norm of A, and also the Lipschitz constant of the domain. All right. So our proof is inspired by the approach in the elliptic case by Dindolch, Hoffman, and Pfeiffer, but with many different, with many new challenges. For simplicity, I will just focus on the case when omega is just a half space, okay? But once we have this, it's not so hard to get to the elliptic setting by a change of variable. So I would just assume that omega is the upper half space cross R. Okay, so the first step we do is to reduce the problem to the block form case. And by that, I mean that, so we have originally the matrix A, okay? And then I will define this A naught, which is you take the first n-1 by n-1 block of the original matrix A, and you put 0, 1 in the last column and last row. So this is an A naught in block form. And what we show is that if our operator satisfies that parabolic Carlson condition, if we know that the regularity problem for this block form operator is solvable, and in addition, if we know the solution to this LP regularity problem for the block form operator satisfies some LP square function estimates on the gradient, then dp prime of the adjoint operator of the original operator implies the LP regularity problem. Okay, so it means that to understand this, we just need to consider, once we prove this theorem, we just need to focus on L naught, which is in block form. So now we want to deal with the block form case. So what we can show is that if the operator is in block form, then we actually get and satisfy the parabolic Carlson condition. Then we actually get the LP regularity problem is solvable for all P greater than 1. Okay, so we first, to show this, we first show that the Dirichlet problem, LP Dirichlet problem for the adjoint operator is solvable for all P. And then we prove the L2 regularity problem for this block form operator, assuming the Carlson condition is sufficiently small. Now here, it's important that we only require that this mu parallel, which is not exactly the same as what I showed you in the beginning, because it's missing out the dxn derivative of the matrix. So we only assume that, so xn now is the distance to the boundary. Okay, so this is this spatial gradient, but also for the first n-1 variable, and the time derivative of a. So we are leaving out the dn derivative of a. So we are assuming that this is a causal measure with sufficiently small constant, and so is this quantity. Now, why is this important? It's because we want to define a new matrix, which is basically, you rescale the xn direction, so we call it AK. So AK is a rescale of the original matrix in xn variable by k. Okay? So what happens is that this new matrix AK is actually a Calson perturbation of the original matrix A, but if you let this k to be sufficiently large, you can make sure that this Calson measure has sufficiently small constant. Okay? So it means that if we use this result by Maltin-Ulmer, who showed basically the regularity problem is stable under Calson perturbation, then we just need to take this k sufficiently large so that we get the L2 solvability for AK with k sufficiently large. Then by the perturbation result, we can say that our P0 for some P0, which it will not be 2, but less than 2, is solvable for the original operator L. Now, once we get this, we can conclude by the duality result, right? Because once we have the solvability of the regularity for 1P naught, then by the duality, we know the regularity problem is solvable as the dual range of the Dirichlet problem. And we show that this is true. The Dirichlet problem is solvable for all P. Okay, so actually, this framework is the same as the elliptic setting, except that on every step here is we have some new terms because of the parabolic equations. However, I want to highlight one major difference between the elliptic case is the following. So when we proved the L2 solvability for the regularity problem for the block form in a small constant regime, and what happens is that we want to show S less than n estimates in L2, which essentially, right, we want to show that this the second derivative of u squared xn is bounded by some constant C1 times the L2 norm of the non-tangential maximal function of the gradient plus the boundary data. Now, what we need is to say that this constant C1 is arbitrarily small if the Calson norm of the U parallel is sufficiently small. It's important because we will later have an n less than s argument, so that if you know this is sufficiently small, then you can hide the non-tangential maximum function to the left-hand side, so you can say that the non-tangential maximum function is bounded by the boundary data. Now, this is the key. Now, how do we get this? Well, since this U parallel, if you remember my definition, it doesn't see the dn derivative of A, we can prove this estimates without so much pain for I between 1 and n-1. So basically here, instead of the full second derivative, we're excluding the dnn of U. Okay? So, but in the elliptic case, sorry, I will finish in 1 minute. In the elliptic case, we can just use the PDE of U and the block form structure to obtain an L2 estimates for the dn and U, and in the elliptic case, that will be the end of the story. but not in the parabolic case, because when we use the PDE, we will have the dt derivative showing up, okay? And to deal with this term, we actually need to go through the square function of the half derivative in time of u, and study the equation satisfied by this half derivative in time of u, which has a non-local term, and we are actually able to control the square function of the half derivative in time in u like this. So we will include the full Gaussian norm, but we are lucky enough to throw in some parameter k, which we can take as large as we want. So many steps later, we are able to show the C1 that I showed in the beginning is bounded by this quantity for any k, and it can be taken as small as possible if we choose k sufficiently large. And I will end my talk here, and thank you for your attention.